Hello friends, I welcome you in lecture number 22 on partial derivatives. In this lecture we will discuss this question on finding the maximum and minimum values of this function fxy equal to x cube plus y cube minus 3xy. This question was asked in GTU Winter 2020 exam. We are familiar with the method of finding maximum and minimum values of functions of more than one variable. So we first find out first and second order partial derivatives of this function fxy is given as x cube plus y cube minus 3xy. Therefore, first order partial derivative with respect to x is derivative of x cube, which is 3x square. This is independent of x, so its derivative with respect to x is 0. Here we consider minus 3y as constant, derivative of x is 1. Del f by del y is x cube is considered as constant, so its derivative is 0. Derivative of y cube is 3y square, and this minus 3x is considered as constant and derivative of y is 1. Then second order derivative with respect to x, which we denote by r equal to fxx. So we differentiate this del f by del x with respect to x again. 3 as it is, derivative of x square is 2x. So we have 3 into 2x, which is 6x minus 0. S equal to derivative of del f by del x with respect to y. So we consider this as constant, its derivative is 0, and derivative of minus 3y is minus 3. T equal to second order derivative with respect to y. That means we will differentiate this fy with respect to y. So here we have 3 into 2y minus 0, that is 6y. We will require rt minus s square. So first we write down r into t, that is 6x into 6y minus square of s, that is minus 3 whole square. So here we will get 36 times xy minus square of minus 3, which is 9. This is rt minus s square at any point xy. And we will calculate this rt minus s square at critical points, which we will find by solving this del f by del x equal to 0 and del f by del y equal to 0. Also we will require value of r, which we have obtained as 6x. R is equal to 6x at any point xy. Now we find out critical points. For that we consider del f by del x equal to 0, del f by del y equal to 0. Del f by del x is 3x square minus 3y equal to 0. Del f by del y equal to 0 becomes 3y square minus 3x equal to 0. We can cancel out 3 by taking common. So here we have x square minus y equal to 0. Here y square minus x equal to 0. 3 is taken common and then cancelled out. This we can rewrite as y equal to x square, and we keep this as it is, y square minus x equal to 0. Now to solve these two equations, we put y equal to x square in this equation. Putting y equal to x square in equation 1, we get y square, that is square of x square minus x equal to 0. Therefore we obtain x raised to 4 minus x equal to 0. Then we take x common, so we will have x into x cube minus 1 equal to 0. Then we write down the factors of x cube minus 1. We have this ready-made formula. We are using the formula of a cube minus b cube. This is equal to a minus b times a square plus ab plus b square. We use this formula with a equal to x and b equal to 1. And we obtain that x cube minus 1 is product of x minus 1 and x square plus x plus 1. So there are three possibilities: x equal to 0, x minus 1 equal to 0, x square plus x plus 1 equal to 0. So from first possibility we will obtain x equal to 0. This factor will give us x equal to 1. And if we consider x square plus x plus 1 equal to 0, we will have complex values of x or imaginary numbers. Complex or imaginary numbers, or we can say that there is no real number x which satisfies this equation, and you can decide that whether roots are real or complex. You can find out this b square minus 4ac by comparing this equation with ax square plus bx plus c equal to 0. If b square minus 4ac is negative, there is no real value of x which is solution of this equation. So if we compare this x square plus x plus 1 with ax square plus bx plus c, we can see a, b and c all are 1. So if we find out b square minus 4ac, we will have 1 minus 4, that is minus 3, which is negative. Therefore there is no real solution, there is no real value of x which satisfy this equation. So we will not consider this possibility, x square plus x plus 1 equal to 0. So we can see, we can write here in the bracket that x square plus x plus 1 equal to 0 has no real solution. So we are not considering that possibility. So there are two possible values of x, 0 and 1. Corresponding to these two values, we can easily obtain value of y using this y equal to x square. So when we consider x equal to 0 in this y equal to x square, we will have y equal to 0, and when x is 1 in this, we can easily obtain that y equal to 1. So therefore 0, 0 and 1, 1 are critical points of f, or we can say that the points at which function can be maximum or minimum are these 2 points, 0, 0 and 1, 1. Now to decide whether function is maximum or minimum or neither of those two at these points, we will use second derivative test. So first we consider this point 0, 0. At this point we find out rt minus s square, which we have simplified as 36xy minus 9. So if we take this rt minus s square at 0, 0, or value of rt minus s square at 0, 0 will be equal to minus. If I take x and y 0, I will obtain rt minus s square equal to 0 minus 9, which is negative. And if rt minus s square is negative at critical point, then function has neither local maximum nor local minimum at that point. At 0, 0 we obtain that rt minus s square is negative. Therefore we can say that function is neither maximum nor minimum at 0, 0, and this type of point is known as saddle point of given function. So 0, 0 is a saddle point of given function, or we can write that function f has neither local maximum nor local minimum at 0, 0. Now we find out rt minus s square at second critical point, which is 1, 1. So we take x and y equal to 1 in rt minus s square, and we obtain 36 minus 9, which is positive 27. And value of r at 1 will be equal to 6 at 1, 1. X is 1. So r is also positive. Rt minus s square is also positive at point 1, 1. So that we have written here Rt minus s square is positive, r is also positive at this point 1, 1. And if r is positive, function has local minimum at that point. Therefore fxy has local minimum at 1, 1, and local minimum value will be equal to value of given function at 1, 1. So we substitute x equal to 1, y equal to 1 in this function to obtain local minimum value. So this is going to be 1 plus 1 minus 3, that is minus 1. Hence function is local minimum at point 11 and local minimum value of function at point 11 is minus 1. So in this way we can easily decide the local maximum and local minimum of a given function using this second derivative test. So this is all about this session. I hope you like it. Thank you very much.